Science is real, from the Big Bang to DNA.
Hi, and welcome back. All right, at this point, you should have a pretty good idea of what I mean when I say reaction order, or the form of a rate law. Also, we've done some good graphing, so hopefully you get the idea of using concentration and time to help us figure out that order, and then using that information to write a full and complete rate law. Finally, we've also used the concept of initial rates and used that to write complete rate laws. But here's the kicker.
There are actually two types of rate law equations. Up until now, we have been studying the differential form of a rate law, which compares rate to concentration. But what if we are doing an experiment and you don't have a good way to measure the rate? No worries. You can use the integrated rate law, which relates concentration as a function of time. Just like the differential rate law changes its exponent based on the order of the reaction, the integrated rate law reveals the order as well. So what does that one look like? Well, unfortunately, the question has to be, what do those look like? Because each order has its own integrated rate law equation. Let's dive right in by looking at a first order reaction. Experience from our in-class practice tells us we will be encountering a lot of first and second order reactions, so it seems like a good place to start. Voila! I present to you a first order integrated rate law. Let's look at it closely, after I take it away first. We start on the left with natural log of the concentration of whatever reactant we are studying. K is still the same rate constant as before. T refers to that specific time. And to the far right, you see the natural log of the initial concentration of the reactant at time equals 0.
Remember, natural log just means you are finding to what power the value E has been raised.
Perhaps you are asking yourself why this equation indicates a first order reaction. To that I say, good questioning. When you think about the relationship this equation shows, it reveals that the concentration of a reactant depends on time, or how far along the reaction has progressed. Remember this graph from our first video? It shows the decrease in concentration of NO2 and increases in the concentrations of products NO and O2. But look at the lines. So curvy. Too much of a bother to analyze in a non-calculus kind of way. But this equation? This equation takes the form of one of our favorite types of graphs. A straight line. So easy to interpret, so friendly to draw. We love you, straight line, and more specifically, when data collected about concentration and time reveal a straight line when graphed as natural log of concentration versus time, we know the reaction is first order. Now I can write my first order differential form of a rate law, since the graph of natural log of concentration of A versus time was a straight line. I know rate will equal K times the concentration of reactant A raised to the first power. Or, notice I can use the negative slope of the line as my value for K in this particular equation. Because slope of that line is the value for K. Well, that's great. That means if we have data to use one form of a rate law, we can use it to figure out what we need to know to get the other type. Well, golly, that's handy, isn't it? But that isn't all. We can actually use this integrated form of rate law to examine half-life.
That's right, folks, half-life. It makes sense if you think about it. When we're studying kinetics, we're studying how fast reactions go. Using the time it takes for half of a reactant to be consumed would be another way to look at that. That's half-life, whether you're looking at nuclear reactions or just regular plain old chemical reactions. So let's start with the first order reaction. Behind me here, you see I've written an integrated rate law for a first order reaction. I'm going to start by rearranging the equation a bit using my rule of logs. So I'm going to subtract the natural log of the original concentration from both sides. This is going to allow me to rewrite the equation to look like this. Natural log of concentration of A over the original concentration equals negative KT. Now, at the half-life, T is going to be denoted by T 1/2. That indicates that is the half-life. And also at the half-life, we know the amount of concentration we have remaining is half of what it was originally. So, in other words, concentration of A is 1/2 of the original concentration. Well, that's handy, because now I can take that and put it in there. So, I'm going to add 1/2 over here, sub 0, because now we're talking about 1/2 of the original concentration. I'm going to divide both sides by negative K to get it on this side of the equation. And now I'm going to make it look pretty. So, scratch that out. I'll rewrite it up here. We end up with T 1/2 equals, well, when dealing with logs, if I divide by a negative, it inverses the whatever we've got up here. So that's going to end up being natural log of 2 over K. And that, my friends, is the half-life equation for first order rate law.
Something very important to notice about this half-life for a first-order reaction. Notice that the half-life at T 1/2 does not depend on the concentration of reactant A, only on the proportionality constant. That means that half-life is constant throughout the reaction progress. Also worth noting here is that all nuclear decays are also first-order reactions. Half-life remaining constant despite a depleting number of nucleons is what makes processes such as carbon dating possible. As promised, we'll play with this idea a little more in class.
Now that we've gone over the first order reaction quite extensively, I'm actually just going to throw the other two you need to know at you straight. In class, we're going to spend a lot of time looking at the equations and using their graphs to analyze their reactions and figure out which orders they represent. But for now, I'd like you to just have a sense of what they are and what they mean. So take a look.
Second-order reactions. You should be familiar with the second-order differential rate law by now. The second-order integrated rate law follows the same y equals mx plus b format, but this time a straight line will be seen when 1 over the concentration of A is graphed versus time. Just like before, the slope of the line will yield the rate constant k. Notice also that this graph yields a positive slope, so no need for negative k as in the first-order equation. As for half-life, well, I'm actually not going to just give this one to you. Sure, you can copy it from your book, but half-life equations are not on your AP equation packet. So you can either choose to straight memorize them or figure out how to derive them from the integrated equations which are on your equation packet. I say go on, give it a try. As I did it before, just start with the idea that at the halfway point, the concentration equals 1/2 of the original concentration. One of you will get the pleasure of showing us your derivation in class. So, be ready. On to zero-order reactions. Raised to the 0th order, the differential rate law is just rate equals k. Zero order means that with respect to that reactant, it does not affect the rate. This will take on greater meaning when we start using this information to predict reaction mechanisms. As for the integrated rate law, straight up concentration versus time. Notice that negative slope again. You're going from a large y to a small y as the concentration decreases. So you need to account for that by having that negative in your equation, since k is going to be a positive value. Otherwise, your rate would be negative according to your differential rate law. See how it all connects? Isn't it beautiful? Half-life. Well, that's on you. Be ready to show the class what you've got.
Well, There you have it. Now you have the basics of rate law under your belt. We've talked about both differential and integrated. However, I've primarily been discussing them in the context of some imaginary reactant A, and we know based on our experience that usually there's more than one reactant. So our job in class is going to be to apply these equations to situations that involve more than one reactant so we can actually figure out how they really work. Just a hint, I foresee a couple labs in your near future. Stay tuned for our next video segment where we actually get to start talking about how we apply these integrated and differential rate laws to predicting mechanisms. See you in class.
Science is real, from anatomy to geology. Science is real, from astrophysics to biology. A